Hi, my name is Phil, and I am a senior lecturer in astrophysics at the University of Lincoln. And I want to use this video to have a look at the transit of artificial objects. Now, lots of my other videos have actually looked at exoplanet detection, exomoon detection, and working out lots of different things about the orbits of an exoplanet due to the transits and the change in those transits that we can actually detect. However, we can apply similar ideas and techniques to look for artificial objects orbiting other stars, things like Dyson spheres, maybe large spacecraft, anything artificial that's not a natural object, we might be able to actually detect using the same techniques that we would use for exomoons, exoplanets, even exorings. But before we do that, I just want to note that in the members section, I do have lots of extra videos that are not available publicly and lots of other benefits. So if you do find these videos interesting and helpful, then do consider becoming a member. And obviously, it does help support the channel in general. So let's just recap what the transit method is. So when we detect an exoplanet orbiting a star, we assume that these exoplanets are orbiting other stars. So the exo part in exoplanets basically means that it's extrasolar. These are planets around other stars, not our own sun. That's actually not the case for all exoplanets. You can get free floating ones that don't have stars, but that's a whole topic for other videos, which I've already done. So let's just assume for this video and for transits that these exoplanets are orbiting other stars. Now, if it's aligned such that that planet passes in front of the star as we, well, basically line of sight from Earth, then it will block out some light. And when it does that, we get a dip in the brightness of the star. So the star gets dimmer. And it's a fairly widely used technique, I should say. It's probably, well, no, it is the technique that has discovered the most exoplanets to date. It's very, very prolific. It's fairly easy to apply. And, well, the problem is we actually detect lots of close-in planets because they actually orbit, the orbital period is quite low. But anyway, let's carry on. Now, if we've got an exoplanet going around the star and it's a single one, then most of those transits look symmetric and they look fairly similar. They occur with a similar time frame between each one. Again, if you've seen any of the other videos where I look at transit timing variation, transit depth variation, those sorts of things, asymmetric transits, that's not always the case, but let's just assume generally a spherical planet on its own, as a general rule, you're going to get a symmetric U-shaped dip in brightness. And the reason for that is as it first starts to transit the star, it's a circle. You've got the area of the planet and the area of the star. It blocks out a little bit of light, then it gets bigger and bigger until it's blocking out the most amount of light midway through the transit. And then it obviously goes across the other side of the star, and then it starts to decrease how much it's actually blocking the light out. So that's why you get this symmetric U-shape dip. So that's the basic shape for a spherical planet. And as you can see, you've got that fairly typical U shape there. Each of those dots on there is an individual image or measurement of the brightness of the star, and then there's a best fit that's been done to that. So the x-axis here will be, it could be in hours, it could be days, it's usually time, or it could be in the actual phase, like the orbital phase. Either way, it's time related, and then your y-axis is going to be your flux, your brightness of your star, essentially basically that. So you get this nice symmetric shape. Now, the transit will change shape. That U shape no longer becomes U shape if the planet's shape also changes. So what we're going to do here is just look at the shape of the planet first before we apply it to artificial shapes. So this time we're going to look at an elliptical shape, or it's actually an ellipsoid shaped planet compared to a spherical one, and how we might know that it's actually ellipsoid and not a spherical planet. So here we've actually zoomed in a bit because on the previous one we couldn't really see it that well. So now you can see kind of, especially midpoint, there's a bigger deviation between the two. And the biggest thing to take away from this is actually at the midpoint when it's blocking out the most amount of light, the elliptical shaped planet or ellipsoid shaped planet is blocking out less light than the spherical one. At the edges it's not quite, the difference isn't quite so much, but in the middle it is. So why is that actually occurring? Well, what you do is if you subtract the two, so what we would typically do is we would take a measurement, we'd get a light curve and a best fit. We would then model a spherical planet, model an elliptical or ellipsoid planet, and then you subtract them. And you end up with this here, which is the difference between those two. And you look for the best fit of what you've actually got in your measurement. So again, here you've got the flux on the y-axis, and then you've got the angle, or it could be that again time. It's just the position round on its orbit. And again, at the midpoint, then your spherical one is blocking out more light compared to the elliptical one. Again, why is that actually occurring? Well, if we are going to assume an ellipsoid planet, it's most likely going to be tidally locked. That it's going to be very close to its star and it's been tidally stretched. So what that means is the ellipsoid shape will be positioned or angled towards the star. So as it orbits around, that will go around its orbit. So it'll always be elongated, basically in a line to the star. So when it's bang in the middle of the transit, the line of sight area that it blocks out light from us as we observe it is actually the least, because it's actually pulled tidally line of sight from us. So it's actually the amount of area that the planet blocks out is less there. So that's why midpoint is blocking out the least amount of light. At the edges, as it starts to transit and as it leaves the other edge of the star, it blocks out more light than the spherical one would do. Now, why does that occur? Again, it's tidally locked, and this is massively exaggerated, by the way. But as it starts to transit, it's slightly angled because that angle is not directly in line with us, if that kind of makes any sense. So because it's slightly edge on, it has a larger area, line of sight between us, the planet, the star. It blocks out slightly more light. So we get this particular signature here. Now, we can apply exactly the same method to artificial shapes. So we actually get that difference between the two models, and we can work out if the planet is ellipsoid in shape or it's spherical. But we can actually detect if it's a triangle, a square, any other shape actually, due to the exact same model, I should say. So how does this work? So let's say we've got a triangle here. And what we would do is we would subtract the spherical model from what we actually got, or we could actually just create two models, subtract them from one another the same as we did before, and then we would get this difference here. And that looks different to an ellipsoid one or an elliptical shaped object that's passed in front. Now, a triangle is not going to be a natural object, that's going to be artificial. So if we got this sort of signal here, signature, we'd expect it to be a triangle. So it is going to require a lot of modeling, a bit more fiddling around, but we can still actually detect the shape of the object that's transited across the star, because it's the difference or the deviation away from the spherical model, which a typical exoplanet, most exoplanets are generally assumed to be spherical. It's only rare cases when they're very close to their star or something else has happened that's been tidally stretched. So depending on its orientation of that triangle, it's going to block out more or less light than a sphere at certain parts of the transit. So it could do more, it could do less. It all depends actually on its orientation. If we rotated that slightly round, then this difference here would have a different order. Maybe it would increase and decrease the amount of light first and then do the next one. So we can actually get the orientation and its shape and its size from the differences between the spherical and the triangle model. Now we can actually work out its rotation as well. If that object is rotating as it goes around, and let's be honest, if it's an artificial object and it's orbiting a star, it's probably going to be rotating as well. And we could get the rotation speed of that by the difference again. And here, because it's rotating, that difference between the two models is going to change more significantly. It's going to show a bit more of a chaotic structure, a bit like this here. Again, so we could actually work out its rotation speed and if the object is even rotating as well, purely from the differences between a static spherical model and a rotating triangle one. And you basically tweak it to get the best match that you could. You can even do more complex shapes. So this one here is like a louver-like 6-screen object. I suppose that's more realistic to what an artificial object might be. No one's really going to be making triangle spacecraft, or are they? This might be more applicable to a large, like, I don't know, space station or something orbiting another star. So you get a bit more of a complex structure, but you could work out the panels in that, or the screens. Again, its orientation, if it's rotating, because you use the spherical model, you create this model and you can create a best fit to it. It's more complex, but we can still get the actual shape of this object doing this. So basically, the whole point of this is the shape of the deviation away from the spherical model can help determine its shape, its rotation, its orientation. So we can get lots of information here about the object. And it doesn't have to be an exomoon, an exoplanet, or anything natural. So we do have the ability to detect artificial objects due to this particular technique. And it could be used to detect technosignatures. And here's like a Dyson sphere, which could be a swarm of lots of spacecraft orbiting a star, which are used to actually subtract or extract, I should say, the energy from a star from an advanced civilization. There could be larger structures, artificially made orbiting stars. So this technique could be used to detect these, which is quite exciting actually. And to date, we haven't really detected anything like that. There might have been some interesting hints in the past, but they've kind of somewhat been resolved. So in the future, we might actually start detecting things like this, hopefully, and that would be quite exciting to then detect these. So thank you for watching. If you've got any questions or any ideas for future videos, then just leave them below in the comments.